Good afternoon. Okay, there's a midterm, was there? And I noticed that every midterm that I ever gave, you can find in any of these course websites where you go. And so people showing me midterms that I haven't seen for a long time. And they say, how does this go? I said, I need to think about this, okay? And so then I decided maybe I should write a new one. Okay, that's what you have experienced. I wrote a new one. Okay, and so it was a little different than all the ones that you have shown me. Okay, so, but it's not the end of the world. So the average out of 70, the mean score was 73. No, not percent. Out of 120. and so all is not lost. Remember, you get 40 points just for coming here. That's on top of everything, okay? You need a 750 points, that's the maximum. You get 40 points on top. And then I give you also 9 if you sort of think a little bit more about your midterm that you just took 2 days before. And I ask you a bonus question. Quite some of you are able to answer that. So there is the final. It will be about 40%, 30 to 40% of the last quarter, the last thing we do here. And the rest will be more or less evenly distributed between midterm 1, midterm 2, and midterm 3, okay? So that's be cumulative. And so there is no need to sort of give up or capitulate. I think you will be just fine, okay? I make what? If I'm going to make the final less difficult. If I ask you, you would say yes. You would say yes. I don't know. It will be less difficult than what? Than the midterm 3? Most likely. Most likely. Okay, this is the last time that I'm teaching Chem 1A. So I have done this for 8 years, so I don't have to worry anymore that my midterms are floating around somewhere. Okay, and so I appreciate you coming here. And I don't know what the reason is that so many of you came to me. Maybe you were looking forward to that midterm. No, not really. Okay, so I will ask that question. Those of you who are just here to click, you need to come back. But I don't know if I do it in the middle of the lecture or at the end of the lecture, the bonus question, because I notice a lot of people, they just click and then they walk away. So this is maybe, so that's why I sort of do this intermittent somehow, in between somewhere or the end, I don't know yet. Depends how my mood is, and depends very much on you how my mood is, okay? So I'm not a very moody guy though. So we have talked about equilibria, and equilibria are, and we talked specifically about heterogeneous equilibria. We have the phases where you have 2 different phases in equilibrium, and we talked about carbon dioxide gas and carbon dioxide in aqueous solution, carbonic acid, and you can write an equilibrium quotient, and if you start out your reaction, you write the reaction quotient. That's the concentration of this here, and this is aqueous, divided by the partial pressure of this, okay? And equilibria are at a fixed temperature. They don't change. If you add products, it will come back in equilibrium. If you add reactants, they will come back in equilibrium to fulfill that K. That's a fixed number, all right? So that's a very important part to understand. And then we talked about barium. Now let me go back to this here. You have barium. Let's look it up here. You have barium sulfate. This is a very insoluble compound. What does this mean? K is what? K is smaller than 1, isn't it right? And it's very, very much smaller than 1. So K in this case, if you look at that equilibrium, dissociates into barium 2 plus ions and sulfate 2 minus ions, SO4 2 minus. So that means that the reaction quotient is the concentration of this times the concentration of this divided by the concentration of barium sulfate. But barium sulfate is a pure solid, and you know this by now. That means it's 1. So the reaction quotient is just the product of the 2 concentrations. And you see here, we call this equilibrium constant the solubility product, because that determines the solubility of this stuff here. And that solubility product is extremely small, 1.1 times 10 to the minus 10. That's extremely small. You can know from this that your reaction is very heavy on the reactant instead of the product. So there's hardly anything of that as BO2 plus and SO4 2 minus. You can say if this is X and this is X here, so this would be the same concentration, then the concentration of barium equals the concentration of sulfate, so that would be the square root out of this here. The square root of 10 minus 10 is about minus 5, 10 to minus 5, and with this the concentration is 10 to minus 5. So if I up the concentration here of barium to 10 to minus 9, if I decrease the concentration of barium times 10 to minus 9, what would be the sulfate concentration? The product has to give minus 10. So that would be 10 to minus 1 then, isn't it? Okay, and so this is exactly what you see here. You have barium sulfate, and you have barium and sulfate ions. They are dissociated, but very little because the K is very, very small. It's 10 to minus 10. And then I ask you, what would I do best if I want to dissolve some very small amount of barium sulfate? Would I add 0.1 molar sulfuric acid? Sulfuric acid dissociates in SO4 2 minus and H3O plus. It's a strong acid, okay? So that means it makes a lot of SO4 2 minus and H2AH plus. And so these are ions. So what if you have sulfate generated? If you add sulfuric acid, you have sulfate here. So you're adding sulfate here. So this is a common ion to your equilibrium. That's called the common ion effect. So if you add sulfate, you make it even more insoluble. You produce more barium sulfate. And if you use barium chloride, it's the same thing. Barium chloride dissociates as an electrolyte into barium 2 plus and 2Cl minus. If you add barium 2 plus here, it pushes it to the left. So the barium chloride the barium is a common ion then, and it pushes it to here, and the sulfuric acid dissociates to 2H plus and SO4 2 minus, also a common ion, and pushes this to here. So what would you use then in order to dissolve a little bit of barium sulfate? What would you use? Water, of course, and this was the answer then. There it is. Okay, so now here is the common ion effect. It's a perfect Le Chatelier's principle example. You have here, if this would be, and this is what I just discussed with you a couple of sentences earlier, barium sulfate, it dissociates into barium 2 plus, that's X, and into SO4 2 minus, SO4 2 minus, and let's go back here. We said we want to add 0.1 molar sulfuric acid, okay? So if you add 0.1 molar sulfuric acid, that would be plus 0.1 plus X, okay? Now, you say the solubility product is this times that. That's X times 0.1 plus X, and we have done something like this, not with solids, in your midterm. So with this, you can now, you know that this is 10 to minus 10. Now you can solve for X, so X is 10 to minus 9. If you add 0.1 molar here, that means the whole thing needs to be 10 to minus 10, so this must be 10 to minus 9. And this is what I just asked you earlier. And so now let's see. If you have ions that are dissolved or dissociated in aqueous solution, they have charges. So they can carry electricity. They are carriers, charges are carriers of electricity. And now, if I have water, and do you think water has a lot of ions in there? Yes, you think it has a lot of ions. Any other thought? Just water. Does it have a lot of ions? No, probably not. If it would have a lot of ions, it would have to conduct electricity. So what I have here is, don't do this at home, I have a light bulb, and there's 120 volts right there, going through the aqueous solution. And so I'm trying to prove to you that this is really a closed circuit. I hope not to electrocute myself. There you go. Okay, and I have this sticking in water. If you could have this up there, please. Okay, can you all see that? Is the light fully on? Yeah, it's good. Okay, so you see here that light bulb. All right, that's the light bulb here. That's the light bulb. And here you see there's two prongs going into the solution, and they are not connected. And of course I have 120 volts here, but because it's not connected, the circuit, I need to connect it with some ions. Ions floating in the solution, then the circuit would be connected. And you have to trust me, difficult now, you have to trust me that the water does not conduct electricity very much. Okay, it does conduct electricity, but not very much. So the bulb is not on. So now, if I have barium hydroxide is a completely dissociates if you put it in water, so it dissociates to barium 2 plus ions and OH minus ions. If I put the solution in there, would it conduct electricity? Would it conduct electricity? Barium 2 plus and OH minus ions? You don't have to shake because of me, okay? Right, I scared the apparatus. Barium 2 plus and 2 OH minus. So that would conduct electricity, wouldn't it be? Okay. Now, if you have sulfuric acid, you have 2H plus and SO4 2 minus. Would it conduct the electricity? Yes, it would. So why don't we put in here? I have here some barium hydroxide, and I have about a 0.1 molar barium hydroxide. I think I should wear my glasses, which I do, but not my safety glasses. Okay, so there's barium hydroxide here. It's going to be loud. Hopefully not. Hopefully. Like Craig Ferguson. Here it is. Okay. All right. And so I put this in here. There it goes. Now the barium ions and the OH ions are conducting the electricity. So now I'm going to do the next thing. I titrate this. I have sulfuric acid in here, and I titrate sulfuric acid in here. What do you think will happen? This will happen, isn't that? The barium will react with the sulfate to make insoluble barium sulfate. What will happen to the light bulb? Okay, it will increase the light, decrease the light. What do you say? What will happen to the light bulb? Decrease the light. Let's see. Let's do that here. I better put this in here. And it's supposed to fit. There it is. And I need to also aim right. That's always important. And then let's start titrating. I have to titrate relatively slowly. Oh, I need to take this off here. So we're now titrating. Is that camera from the front? Yeah, okay. Nothing happening. Yeah, that's what happens with titration. And then you go to the equivalence point. Whoop, you are above the equivalence point. Did you do that in lab? Yes, exactly. If you need to really titrate slowly, then first of all to let it react. That's the first thing we need to steer it somehow. Okay. You see that white stuff in there on the bottom? That's what is that? Barium sulfate. All right. Let's be quiet here, okay? A little bit more. So I better need to lay down here. Nothing's happening, huh? They're getting darker? There it is, huh? Yeah, I don't want to chance it, actually. What happened? Did you see what happened? Okay, so can you tell your neighbor, please, what happened? Where's my water? Is it, the light bulb is off now. Do you see that? Okay. Now, let me ask you a question. So I'm not finished with this titration. Okay? I'm not finished with this titration. Actually, I'm German. Never mind. Never mind. So you have this barium hydroxide with the sulfuric acid, so the barium and the OH minus with the sulfuric acid, you titrate it, so you made obviously barium sulfate. And then I have, is it what we just did this here? But I'm not finished with the titration, okay? So when I'm finished with the titration, will this look like this here? Will this look like this? That means that the light bulb went dark here, okay? That's 0, and this is high light bulb, or bright light bulb. And will it look like this, or will it look like this? Stay dark. Why don't you think about this and give me your answer, please? What will happen if I continue titrating? So this is off here, and I have white precipitate here. Pardon? No, the barium sulfate is white. Barium sulfate is white. Yeah, if I'm not finished with that, if I continue adding, what happens? What's going to happen? What's going to happen? Good. Okay, we have a discussion here. That's fine with me. Actually, the last time when I apologized to you at the end, you were not the ones who made the noise. These were all these guys outside who were coming in for their midterm. So I apologize again, but I sort of had the feeling that you were totally unruly, you know, and these were all these guys outside. Beg your pardon? No, there's no curve. Okay, there's a majority goes for B, but sort of the other two are equally, not quite, more for a C. So nothing happens. A majority says the light will go on, and some of them nothing will happen either. But I will not do anything with sulfuric acid. So that is not quite right. So why don't you discuss this with each other now? Really discuss it, please. And let's see. You need to really understand that. amplified. Yes, you students are very good. Okay. Now, it got to be B. Now, let me prove you. So now we have precipitated all the barium with the sulfate, okay? It's all gone. It's all barium sulfate. So there's a very small equilibrium constant now, all right? It's 10 to minus 10, actually. And so there's hardly anything in product, anything dissociated. So now if I keep titrating here, let's see, do it elegantly. Come on. I need a little faster. There you go. There it's dripping. So what happens? Now I'm adding nothing but sulfuric acid because it can't react anymore with the barium, and the other light's going to get on and gets brighter and brighter until I have reached, there you go, it's brighter and brighter now. What does the conductivity, what's due to what carries the electricity? That's the ions of SO4 2 and H plus, okay? All right, good, you have understood it. Let's see if we can get it even brighter. No, that's it. All right, good. So we need to solve that equilibrium here, but first I need to be quiet, okay? Right. All right, there we go. We did the result we did already, huh? Yes, I said that you were good. And so that's what we added. After barium sulfate is produced, we precipitated that. There's no more barium in there. So this is our new equilibrium. And I'm just adding sulfuric acid that dissociates as a strong acid, dissolvates to SO4 2 and A2H plus. And with this, the electricity will be conducted. And this is the graph here. This would be the light off, and this wouldn't make any sense here. Okay? All right. So today we're going to talk yet about another equilibrium. It's nothing special, but it's a very important equilibrium because it's also very important in our body, the regulation of acid and base in our body. If you are pHs, and you will learn what this is today, if your pH is just off a little bit of your blood, for example, you're in severe trouble. No, by even a tenth of a pH, you're getting in severe trouble. That means pHs in our body are very, very, very finely regulated in order to have certain reactions that drive us. And with this, I'm going to talk about acid and bases. And when you think about an acid, and in the old days, you went to high school probably, and some people, they're homeschooled, okay? And so you went to high school, and some of your teachers, the chemistry teachers, they told you, an acid is that when you put it in water, it produces H plus. And the base, if you put it in water, it produces OH minus. Who was taught that? Okay. Smells burning. Oh, my God. Burning the dark. I'm sorry. I have an emergency here. I have to tend to. Okay. Good. No, we don't need clarity. Just we keep the fireman away. So, all right. So I put the heater on there, but things happen. So that was sort of what they knew about the end of the 19th century. Okay, that's that's the definition by Svante Arrhenius, and they taught you this in high school. There's a much better definition. That is the definition that was by some Danes and the Swedes. That was there's Bronsted and there's Lorry and Bjerrum. Actually, two of these guys discovered this, and the other guy discovered it independent from them. And he said these are now the Bronsted acids. The acids are compounds that donate hydrogen ions, and bases are compounds that accept or pull away hydrogen ions. So that's a very different definition than the Arrhenius definition, and this is the definition that we're going to be using. It's a relative modern definition. It's only 50 years later, actually. It's the beginning of the 20th century. In 1927, they came up with this. And so what you have here, HA, we call it generic. That's an acid, and it has a proton. Acids have protons. And then you have a base. And I defined this. An acid can give away, donate hydrogen ions. So if I donate a hydrogen ion, so I have then hydrogen ion means it is just the proton itself. That's why I call it also proton. And proton or hydrogen ion or hydronium ion is essentially all the same. It's all semantics, okay? It tells you that it's an H plus or an H3O plus. It's essentially the same, okay? So this is my acid, and this must be my base then, because the base wants that proton from the acid. The acid says, okay, I give it to you, all right? Now, when I do that here, then suddenly I have the hydrogen ion is gone here. This is now a base. It's a conjugate base. That is my acid, and that's its conjugate base here. And now this was the base, but it took that hydrogen ion now, and it becomes a conjugate acid, all right? And if you have a strong acid, then it likes to give away, and this is the definition of strong acid, it gives away very easily the hydrogen ions. It has a very, very large K for this reaction here. The K is for hydrochloric acid, for example, is 10 to the 7. Yeah? And if it's a weak acid, it doesn't give much away. The equilibrium is more on this side than on this side here. That's the difference between weak and a strong acid, and we will discuss this in more detail in this lecture and in the next lecture. So you have, let's see if we can do that here. If I could have the lights, please. And I need one person. So I'm now, this is my hydrogen ion. What am I? No. Okay. What am I in the sense of chemistry? What am I? I have a hydrogen ion. I'm an acid. Can you be my base, please? Okay, so you want this. I want to get rid of this. Now what is he? He's the conjugate acid. No. He's the conjugate. No, not true. I'm the acid. Okay? Now you take this from me. What am I now? I'm the conjugate base. What was he? He's the base. What is he now? The conjugate acid. You get that? So there's always an acid-base pair. So if I'm a strong acid, then I try to get rid of this. Okay? Okay. And so he is now hanging on to the hydrogen ion, and he's now a lousy base, a very weak base, because I was a strong acid. The conjugate base of a strong acid is a very weak base, exactly, because he's hanging on to his hydrogen ion, so he can't do anything about this. So if I'm a weak acid, that means only a couple of those will go to him, and the rest I stay with me. So the equilibrium is very much on the acidic side. So that means the equilibrium constant is usually smaller than 1, okay? So we will talk about this. All right? Now, what are you compared to me?